For decades, military engineers have worked to compress the destructive power of a nuclear weapon into a practically usable, precision-guided format for the modern battlefield. This effort yielded tactical nuclear weapons, or TNWs. Unlike strategic warheads designed to level entire cities, TNWs are low-yield devices, generally under 15 kilotons, built for specific, localized combat operations. This technical drawing details the historical W-48 artillery shell. It measured 15 millimeters in diameter, 34 inches in length, and weighed exactly 120 pounds. Despite its small size, the W-48 delivered a yield of 100 tons of TNT. It was built to provide divisional commanders with immediate, close nuclear fire support. Today, the successor to battlefield artillery is the B61-12 gravity bomb, developed under the Life Extension Programme and deployed from modern stealth platforms like the F-35. This breakdown shows the B61-12's core advantage. A steerable tail kit guidance assembly achieves a 30-meter accuracy radius. It also features a dial-a-yield function, letting operators select the exact explosive output from 0.3 up to 50 kilotons. While engineering has made delivery systems physically precise, it has not altered the underlying physics of a nuclear explosion. That physical reality creates an immediate conflict with legal requirements. Any use of military force, including the deployment of tactical nuclear weapons, must comply strictly with international humanitarian law, or IHL. In 1996, the International Court of Justice, the principal judicial organ of the United Nations, issued a landmark advisory opinion on the legality of nuclear weapons. The court concluded that the threat or use of nuclear weapons is generally contrary to the rules of international law applicable in armed conflict. The court left open one major caveat. They could not definitively conclude whether nuclear weapons would be lawful in an extreme circumstance of self-defense, specifically where the very survival of a state is at stake. A recent working paper from the Joint Chemical, Biological, Radiological, and Nuclear Defense Center of Excellence analyzes whether modern tactical-scale nukes can actually satisfy the legal demands of that extreme self-defense scenario. To pass legal scrutiny, a weapon must satisfy the principle of distinction. This customary rule requires that military operations only be directed against military objectives and combatants, never civilians. It must also satisfy the principle of proportionality. This prohibits attacks where the expected collateral damage to civilians is excessive compared to the concrete military advantage anticipated. Establishing the legality of a tactical nuclear strike is therefore a mathematical calculation. It is dictated entirely by the physical reach of the explosion's effects. This 3D topographical map establishes the parameters for the legal simulation. We will model a 10-kiloton warhead detonated over a neutral environment, with a defined military target adjacent to a civilian inhabited zone. A nuclear detonation releases energy through 4 primary channels: blast overpressure, thermal radiation, prompt ionizing radiation, and residual fallout. The blast wave and the thermal radiation flash expand outward instantly. Together, these two forces cause the vast majority of immediate mechanical injuries and severe burns. To understand the baseline damage of this yield, we look to the Little Boy atomic bomb dropped on Hiroshima, which had an estimated yield of 15 kilotons, often used as the benchmark for a tactical strike. At Hiroshima, the combination of these physical effects resulted in approximately 68,000 fatalities, destroying nearly everything within a 1-mile radius. Environmental factors like weather and terrain alter these effects. In extremely cold conditions, the reach of lethal thermal radiation increases by as much as 30%. For a 10-kiloton strike to be legal, these radii must be strictly contained within the target zone. That containment is dictated entirely by the height of the burst. Simulation Scenario A models a 10-kiloton high-altitude airburst, detonated at a minimum of 140 meters above the target. This profile of a 10-kiloton airburst shows why 140 meters is critical. It is the lowest altitude at which the resulting fireball can reach its maximum expansion without interacting with the ground. Detonating at this altitude carries a strict mathematical consequence. The strike produces no immediate long-term radioactive contamination or residual fallout. While the blast and thermal radii are maximized for surface destruction, Their footprints are geometrically predictable and contained entirely within the target zone. The JCBRN study concludes that this is the cleanest and most precise detonation possible for a 10-kiloton warhead. By preventing uncontrollable fallout plumes, the airburst is the only scenario that theoretically complies with the principle of distinction. Modern militaries often require specialized earth-penetrating delivery systems to neutralize deeply buried command bunkers or hardened subterranean facilities. This requires scenario B and C, the surface burst and the subsurface detonation, where the fireball physically interacts with the earth. This 3D map visualizes a surface interaction. The fireball instantly vaporizes rock, carving out a nuclear crater and injecting irradiated debris into the sky. This debris becomes residual fallout. Wind carries it far beyond the impact point, drifting continuously over populated areas. Unpredictable meteorological factors, such as temperature inversions or sudden rain, force this radioactive material down, concentrating the fallout over civilians miles away from the target. Because fallout cannot be perfectly predicted or geographically contained, ground and subsurface bursts inherently violate the principle of distinction. Any tactical advantage gained by destroying an underground bunker is legally voided by the indiscriminate nature of the resulting radioactive plume. Even the theoretical legality of the clean airburst fails when we account for prompt ionizing radiation, a physical effect present in every nuclear detonation. This map highlights an invisible radiation wave. Prompt radiation is released instantly and extends far beyond the localized blast radius, penetrating structures and causing severe cellular damage. The biomedical effects of this exposure are severe and enduring, leading to leukemia, thyroid cancer, and life-shortening damage to connective tissues. Exposure introduces severe biological disparities. At the exact same radiation levels, healthy females face a significantly higher risk of lethal cancer than males. Because this biological damage is unpredictable and widespread, calculating proportionality becomes a mathematical impossibility for military planners. There is no accurate way to weigh the concrete military advantage against the exact collateral damage. Radiation damage is invisible, unpredictable, and intergenerational. It erases the concept of a contained military strike. The JCBRN study concludes that while an airburst is the least problematic method of deployment, any nuclear detonation will likely violate the provisions of international humanitarian law. A guidance tailkit can steer a bomb to a precise set of coordinates, but precision guidance cannot control wind drift, atmospheric pressure, or the human body's biological response to ionizing radiation. The engineering goal of absolute battlefield usability remains incompatible with the legal prohibition against indiscriminate effects. Modern engineering has successfully refined the physical hardware of the weapon, but the chaotic physics of radiation and weather render its deployment an operational paradox. To the modern defense analyst, the tactical nuclear weapon is a technologically precise instrument that remains legally unusable in almost every battlefield scenario.